Okay, so this is going to be the exam 1 review for Module 3. When we first started Module 3, right, we did the box problem for 3.1. In our version, we cut out we cut out all 4 corners from our piece of paper to make a box. But this problem from your review was a little bit different, right? This one is saying that we have a 15-inch by 12-inch piece of paper, or it says cardboard actually. But this time we're going to construct the box using the corner of the room. This means we can create the box by just cutting out a square from just one corner of the cardboard and then using the sides of the room to go along with the box. So honestly, what I did for this problem to really kind of understand it was I literally just grabbed a piece of paper and I cut out one corner. And then I tried to follow along and make this box. And I think if you do that, that'll definitely help kind of visualize what's going on with this problem. So for part A, it says, determine the function f that expresses the volume of the resulting open top box in terms of the size x of the one cut out corner. So what this is really saying is we want to determine the volume, but we want to do that using f of x. So it's where our f of x equals our volume, okay? And then as a reminder, what you'll need to know is the volume of a rectangular prism, which is length times width times height. So when we look at this piece of paper, okay, we know that the length is 15 inches. We want to find out what is our length of the paper when we cut out x inches from the side, right? So that's just going to be 15 minus x, because we're only cutting out one corner. And on this side, right, we know the width is 12 inches. So we want to figure out the width after we cut out the other side of the corner, right? So that's just going to be 12 minus x. So now we have our length and our width. And then if you guys remember from in class, right, whatever we cut out from the corner, right, our x, our length of the side of the cutout, is going to be our height. So when we have volume, we will have that f of x equals 15 minus x times 12 minus x times x, okay? And then we have part B. So part B says, what is the domain of the function f from part A in the context of the problem? So that part is important, right? It says in the context of the problem. So if you have a piece of paper, okay, and we want to take a look at the domain. In this case, our domain is going to be all of our possible independent variables. So we know our independent variable here is going to be x, x being the length of the side of the square cutout, okay? So we have to figure out what are all the possible values of that. Well, if we have a piece of paper, we want to take a look at the shortest side, because when we're cutting that, that's going to kind of become a part of our restriction. So if I'm cutting out over here, right, an X amount of length, this time I'm only cutting out one corner, so I do not have anything else happening on the other side. This is remaining the same. Okay, so I'm only cutting from this side. So as I'm cutting, let me change the color, right? I can have 0, like I can leave the paper just as it is, or I can keep cutting all the way over here until there's literally nothing else to cut. I've cut the entire thing, and that would be at 12, right? 12 inches. So our domain would be from 0 to 12, okay? And then for units, right, we're using inches because we're talking about lengths. Okay, so now we're going to move on to part C and D. So part C says, what is the range of the function f from part A? Okay, so to do that, we're going to have to go into Desmos and look at it. But before that, I want to talk about range in this problem, right? So range would be all of our possible dependent quantities, okay? In this case, x was our independent quantities. So that means f of x, right, is going to be our dependent quantities, also known as just our volumes. Okay, so I have already put it into Desmos, and you get a kind of crazy graph like this. Okay, but we have already kind of restricted the domain in terms of the context of our problem, right? We know that you can either be you can be from 0 until 12 inches for the domain. So we only want to look at y values in this interval. But then there's also one more thing you have to consider, and that's the fact that we can't have negative volume, right? So we don't really care about anything that's happening below the x-axis, because we know the lowest volume realistically that we can have is 0. So we want to figure out, okay, well, what's the highest volume that we get with this box? So to do that, you're going to scroll all the way up, again, staying within that interval from 0 to 12. And this is our highest point right here. So from that, we can see that our highest volume that we have is around 354. So when I go back over here for volume or for range, we're going to say, okay, well, the lowest we can have is 0 up until 354. And then it says round to the nearest 3 decimal places, so that's 468. For units, right, since we're dealing with volume, our units are going to be cubic inches. Okay. Part D, what value of the cutout length x will produce an open top box with the largest volume? Well, we kind of already figured that out. When we have our largest volume of 354, the associated x, our length of the side cutout, is 4.4. So it would say, well, that's just going to be 4.4174 inches. Just like that. So now we're going to get into 3.2, which we go a little bit deeper into domain of our functions, okay? So just to clarify, right, domain would be the values the independent quantity may assume, and range is the values that the dependent quantity may assume, okay? So one of the key things for domain was this description from your workbooks, right, that I really liked. So this kind of helps us when we're dealing with domain questions that are not like in context problems. There's certain rules we kind of have to follow to be able to correctly talk about our domain, right? So if we have a function, the first thing it says is it is not possible to determine a real number square root of a negative number. So what that's saying is we don't want to have any negatives under our square roots. That wouldn't be a valid part of our domain. We'd have to restrict it, okay? Also, the denominator of a quotient cannot be 0. And then part 3 is just talking about the in context stuff that we kind of just went over on the other problem. So for an example, I was going over number 9 from your review. Okay, so the first one was A. And to do this, right, we take a look. We have both a square root that we're dealing with and a fraction, so we're dealing with the denominator. So there's a couple things we start by looking at. And the first one is, right, when is this function undefined? So I'd say it's undefined when. Okay, and let's look at it. So we know that we do not want any negatives under the square root. So it would be undefined when x is less than 3. Okay, it's okay for x to be 3 because we can have a 0 under the square root, but we don't want it to be less than 3. So if it was 2, for example, 2 minus 3 is negative 1, and we don't want that because that's the square root of a negative number, and we can't have that. Okay, and then we have the denominator, and so it would be undefined when x equals 10. Because 10 minus 10 is 0, and we do not want a 0 in our denominator. So then when we're talking about domain, right, this is just what's undefined. When we're actually talking about domain, that means we want x to be greater or equal than 3. Okay, we want that, that's okay, as long as it's not less than 3. But then we also want, we don't want x to be equal to 10. So these are the things that would be included when we write our domain. Okay, so the first thing is domain, and I'd say, well, the lowest value that we can have in our domain is going to be 3. And I put it in brackets because that's included. We can include 3. But again, we don't want anything less than 3 to be included. And then we also just don't want it to be 10. So we put 10 here, and we use parentheses to emphasize that 10 is not included. We use our union, and then we would go from 10 to infinity. So what this is saying is that our domain is going to have a lowest value at 3, and then it does not include 10, but it can be anything greater than 3 that obviously isn't 10. So that's basically what this is saying. And for infinity and negative infinity, we always use parentheses because those are not technically included. So then now we had part B, pretty similar thing. So I start out by saying, okay, when is this undefined? So undefined when? Well, we have a denominator, and again, we don't want that to be 0. So it's going to be undefined when t squared minus 9 equals 0. So what t value is that? Well, we have to solve for it. So we'd say plus 9, t squared equals 9. Then you take the square root, and then you have t equal 2. But when you take the square root, okay, you always have to do plus or minus whatever that is. In this case, it's going to be 3. And basically what that's saying, right, 3 squared is 9, but negative 3 squared is also 9. And here in this case, our function would be undefined at both of those t's. So when we talk about our actual domain, we do not want t to be equal to 3, and we do not want t to be equal to negative 3. So our domain can be any real number except 3 and negative 3. So the way we write that is it can be from negative infinity all the way up until negative 3, parentheses, because we do not want to include that in our domain, union, negative 3 to 3, which, right, this part just means anything in between negative 3 to 3, but not including negative 3 and 3, and then union, 3 until infinity. Okay? Now, we have our last one over here. So, again, we talk about when is this undefined. So this is undefined when it's a square root. So we don't want to have any negatives under the square root. So this would be when 2a plus 7 is less than 0. So just like before, we're going to solve for a variable. So minus 7, 2a is less than negative 7. Divide by 2 on both sides. Okay, so a would be less than, as a decimal, this is negative 3.5. So that's when it's undefined. That's what we cannot have in our domain, right? So we go over here. It can't be less than negative 3 or 3.5, but our a can be anything greater or equal to negative 3.5. So then our domain is just going to be all real numbers that are greater or equal to negative 3.5. Thus, our lowest a value is negative 3.5, and it can be included since we have this equals up until infinity. Next up, we have function notation from 3.3. So there's a couple things I want to talk about. This was the definition pulled from your workbook, and this was referring to the box problem we did where we were cutting all 4 corners. But the principles are the same here, right? So they're saying let x represent the length of the side of the square cut out in inches, and v represent the box's volume in cubic inches. So what they did here is we have a function, okay, called the relationship between these quantities f, where x represents the input values and v represents the output values. So that's super important when understanding like what function notation means, right? So we're just setting volume equal to f of x. And then we have our regular rule that we wrote out before. And then it's super important to understand the parts here, okay? So, right, x is our input. F of x is our output in the same way that volume is also our output. And then the entire thing is just what we call the function definition. with this part of the expression being the rule. But just remember, right, x is our input, and f of x is our output, and that's super important. So I pulled number 8 from your review guide that we can kind of talk about. An example of just using function notation. This would be an average rate of change example, but I selected it because it's talking about, well, it's using function notation. So we have let d be the distance in feet of a race car from the starting line, and let t be the number of seconds since the race began. So I'm going to underline that. So the distance d is a function of the time t and is represented by the function f. So what they're saying here, right, f of t is equal to this expression. And then f of t is equal to d, our distance. So part A says, what is the meaning of f7 minus f of 3? Well, we talked about this, right? F of t, whatever that t may be, is equal to our distance. It's our output. And our input t is just our time. So right, it's 7 seconds and 3 seconds. So what is the meaning of f of 7 minus f of 3? Well, f of 7 minus f of 3 represents the change of the distance traveled, right? Because f of 7 and f of 3 are both distances, right? So this is the change of the distance traveled by the race car as time changes from, right, we're at 3 seconds and 7 seconds. So as time changes from 3 seconds to 7 seconds. So I hope this is just making it clear, right? When we say f of t, this is our output. In this case, it's our distance, where t is our time. And obviously, if you were actually defining these, you need to be more specific, in the same way that they defined it right here. D be the distance in feet of a race car from the starting line, and t be the number of seconds since the race began. So in reality, t I would actually just write as number of seconds. And the distance you can just follow from the equation or the problem. So for part B, compute the race car's average speed over the interval t equals 3 to t equals 7. So the main point I want to make here is just how to write average speed using function notation. Okay, so the distance, the change in the distance, we already know is represented by f of 7 minus f of 3. So we have f of 7 minus f of 3, and our change in time is just 7 minus 3. So that's how you'd represent the average speed using function notation. Now, if we went through and actually solved it, right, you would have to say, okay, well, what is f of 7? F of 7 is going to be 3.2 times 7 squared plus 3 times 7. Just plugging 7 in to our equation over here. And that's going to equal 177.8. You would do the same thing for f of 3, right? F of 3 is just going to be 3.2 times 3 squared plus 3 times 3, which is going to equal 37.8. So if we come back over here, right, f of 7 minus f of 3 is really saying 177.8 minus 37.8. 7 minus 3 is 4. And then if you solve this, you would get that it's 35, and then make sure you use units, right? It's going to be feet per second. Part C is just asking us to describe the meaning of average speed in this context. And I've talked about this a lot in class, right? But let's reiterate. So the average speed here is going to be, this is the constant speed that a car would need to travel, right? I want to emphasize this. The constant speed that a car would need to travel in order to cover the same distance in the same time as the race car did. Okay, so the average speed is kind of our estimation to figure out what the constant speed would need to be to cover the same distance in the same amount of time that the race car actually did. Okay, so now we're going to move on to 3.4 and 3.5, which was function composition. So the key parts of the definition here that I think we should focus on, right, is that it's saying if f and g are functions, then f of g, remember this is another way, like we can write the name of a function composition, okay, is the name of the composite functions formed by chaining together the two processes. So it says, right, if we input a value into g, we would get an output value. Then we use that output value of g as an input to f. And then we get another output value. That output value is just going to be the output for the entire composite function. And then again, just to reiterate, f of g is the name of the composite function, and f of g of x represents the composite function's output value. So it's important that you are able to associate those two together. For this one, I pulled number 49 from the review sheet, so we can kind of look at graphs and composite functions. The first one, A, it says compute g of f of 1. So the first thing we want to do is, okay, well, what is f of 1? We look, the blue graph is our f. So f of 1, when our x is 1, our f of 1 is going to be equal to -2. So with an input of 1 into f of x, right, we got an output of -2. We take that output, and that's going to be our input into g, right? -2 just goes right as an input for g, and we find what that is. So what is g of -2? Well, we look over here at the red line. When x is -2, we look, and our y value is 10. So what that means is g of f of 1 is going to be equal to 10. So now we'll do the same thing with b. So the first thing is, what is g of 4? Well, g of 4 gives us, right here, right, a y value of 4. Or, I'm sorry, an output value is what we should say. So we take this 4, this output value becomes our input value for f. So f of 4, let's find what that is. So f of 4 is going to give us, looks like it's over here, right? So 13. What does this mean? Well, that means our f of g of 4 is equal to 13. Now we look at C, this one. It's using f of f. So we're going to be focusing just on this blue line right here. So the first thing is, okay, what is f of 2? Well, f of 2 looks like it's 1. And then we say, okay, what is f of 1, right? Because this output becomes the input for our outside function. So f of 1, well, we already know what that is, right? F of 1 was equal to -2. So f of 2 is equal to -2. Alright, so next up we are continuing function composition. I know a lot of you had questions on this problem, so I pulled it from review number 26. So we're given a circle with a square inside of it, and we are asked to determine a formula which expresses the area of the circle in terms of the length s of the side of the square. So first thing, right, it says determine a formula which expresses the area of the circle. So if we look at our equations that we have right here, area of a circle is represented by pi r squared. But this wants it in terms of s, the side length of the square. which is given right here. It's given that, I'm going to say, right, S equals square root of 2 times R. So if we want to represent R in terms of S, all we're going to do is isolate R from S equals square root of 2 times R. To do that, we're going to divide both sides by square root of 2. So we're left with R equals S over the square root of 2. So it's rewritten so that it's the radius in terms of S, the side of the square. So if we go back over here, for the area, we have pi, and then instead of R, we're going to say it's S over the square root of 2 squared. And that's really what we have for area. But then you're going to want to remember that you can simplify here. So you can just use like your exponent rules that you should know, right? And so we have this squared that we can put to the numerator and denominator. So we would have S squared over square root of 2 squared just means we cancel the square root. So we have a 2. And then we're still multiplying by pi. And since you're multiplying the fraction, you could put it in the numerator like this. And that's how they got the simplified answer of pi s squared over 2. For part B, determine a formula that expresses the circumference of the circle in terms of the length s. So the circumference of a circle was 2 pi r. When it says in terms of the length s, which luckily we already have r in terms of s, so we can just use that one. So instead of r, we're going to say s over the square root of 2. But again, you're going to have to simplify. So if I rewrite this, like putting our multiplication stuff in the numerator, right, I have 2 pi times s over square root of 2. The problem with this is that there's a square root at the denominator, which we don't like. And so if you remember, the way to simplify this is to rationalize your equation or formula. So to rationalize, you multiply the top, bottom of the fraction by square root of 2. So what you have left is 2 pi times s times the square root of 2 over, when you multiply square root of 2 times square root of 2, similar to before, your square root it cancels out, and what you're left with is 2. You can even test that on your calculator, right? Square root of 2 times square root of 2 will leave you with 2. So here we can simplify further, right? Our 2's, since we're multiplying everything in the numerator, we can cancel out the 2's right here. So we're left with square root of 2 times pi times s. Like that. So again, you just have to review, how to simplify things using your algebraic skills that you have coming up. So for part C, determine a formula that defines the area of the square in terms of the circumference, C, of the circle. So let me change colors, right? Area of the square is 2r squared, but it wants it in terms of the circumference, not the radius. So if I look at circumference of a circle, right, we can go to the side again. That's C equals 2 pi r. But now, since our area of a square inputs radius, we want it to instead input circumference. So we can look at this equation and rewrite it so that it's radius in terms of circumference. So to do that, we're going to isolate the radius. So you divide by 2 pi on both sides. And r is going to be equal to c over 2 pi. So area of a square, we know that that's 2r squared. But instead, we're going to say 2 times, right, in terms of circumference. So we can use that r equals c over 2 pi. So it's c times or over 2 pi squared. And then we're going to simplify. So again, you want to use the power rule for your exponents. And we're going to have that this is 2 times c squared over 2 squared is going to be 4. And then with the pi, we can just leave it as pi squared because we don't really want to deal with like all the decimals that come from that. And then you'll have that. And your last step is going to be just to move that 2 or multiply it with the numerator. So 2 times c squared over 4 pi squared. And then there's one more thing you can do because you have a 2 and a 4. You can simplify even further, right? And you're going to be left with c squared over 2 pi squared. Cool. So now that's that for the function composition. We're going to move to 3.6 inverse functions. So this definition that I pulled, right, it says that a function and its inverse relation represent the same relationship between two covariant quantities, but with the independent input and dependent output quantities reversed, right? And what it says here, right, if function g is the inverse of function f, then g undoes the process of f, and f undoes the process of g. So we can jump in. We're going to see some examples. So this first one, right, is kind of getting at, this is number 6 from your review sheet, the meaning of what the function notation represents, and then what the inverse of that function would represent. So the first one is, what does the expression 3 times g of 6 represent? Well, let's read the problem. So suppose the function g represents the cost of tuition at ASU T years since 2000, and that tuition has been rising each year since the year 2000. So, right off the bat, it says G represents the cost of tuition at ASU T years since 2000. So to represent that using function notation, we would say G of T, right? Where T is our years since 2000, and G of T is going to be the cost of tuition at ASU T years since 2000. So, based on what we've kind of talked about before, we have to talk about, okay, well, what is G of 6? Well, given this context, right, or what we have been talking about, G of 6 is going to represent the cost of tuition at ASU 6 years since 2000. And then you're multiplying that by 3, and a lot of times we've said that as, oh, this is going to be 3 times as large as the cost of tuition at ASU 6 years since 2000. But the answer for this problem from the key, it represents it a little bit differently. I think they're taking it into account that this is the cost of tuition per person at ASU. So if you're doing it in the context of that, that's how they got to the point that 3 times G of 6 represents the cost of tuition, right? Because it's our output at ASU for, now if I'm saying that this originally, this G of T is for one student, when we say 3 times G of something, that would be for 3 students. So for 3 students in the year, right? Well, we know that 6 is our T, and it's 6 years since 2000. So since the year 2006. Now, what does the expression G inverse of 15,000 represent? So if we remember from our definition, right, a function and its inverse represent the same relationship, but the independent and dependent quantity is reversed. So in this case, right, our independent quantity was T, years since 2000. But now if we're looking at the inverse, our independent quantity is now instead the cost of tuition at ASU. So when we say, what does the expression G inverse of 15,000 represent? Well, that represents the number of years after year 2000 in which tuition cost is 15,000. So again, let's go over this one more time, right? when we look at 3 times g of 6, our input quantity is t years since 2000. And focusing on this whole thing, right, our output is the cost of tuition given that many years. But when we have the inverse, our input, let me just switch the color. Our input, right, is actually going to be the cost of tuition at ASU since however many years. But our output is actually what represents that number of years. So it just switches. Okay, so now we're going to be looking at still function composition and function inverse or inverse functions, but I want to make sure we understand how to find certain values using both a table and a graph. So the first one I pulled was number 7 using the table, right? And this is going to include both function composition questions and inverse functions. So we look at the first one. We're given this table, right? We have x, f of x, and g of x. So the first one says to determine g of f of 2. So since this is just a regular composition function, right, we know that 2 is the input to f of 2. So we would have to find what is f of 2. If 2 is the input, right, we're going to look at our x's, and we're going to look for number 2 right here. Number 2. And we want f of 2, which is right here, -1. So then g of -1, similarly, right, we want x is -1, and then g of -1 is 2. So then g of f of 2 equals 2. The next one is super similar. We're going to do the same thing. So -2 is our input here. So f of -2. When we have -2, our f of x is 2. And then we would say, okay, this now becomes, right, my input into the g of x function. So we're looking for g of 2, where 2 is our input, so we can look at the x. And we find 2 again right here. What is g of x? Well, that's 1. So that's g of f of -2 is equal to 1. So that's the normal, like, function composition stuff. But over here, right, we're going to get into inverses involved in function composition. So right off the bat, g of 0, that's just a regular function. There's nothing crazy about that. So we want to look for what g of 0 is, given our input of 0. So when x is 0, g of x equals -1. Now we have f inverse of -1. I don't know what that equals. Well, our table, it only gives us f of x and g of x stuff, right? But if we have f inverse of -1, that means our input to f inverse is actually our output with f of x. Okay, so again, the input to our inverse function of f is actually going to be our output when we're looking at f of x. So the first step is, we're kind of working backwards here. The first step is, where is f of x of -1? Or, I'm sorry, where is -1 with the f of x row? That's going to be right here. And we want to find what that x value is, which is just going to be right there, 2. This guy. So f inverse of g of 0 equals 2. Now we move on over here. So we have g inverse of 0. So again, if 0 is the input to the inverse of g, that means it's our output for g of x. So g of x is 0 right here. And what's the corresponding input for that? Well, when g of x is 0, we know that our x is -2. So now we would do f inverse of -2 and do the same thing. Again, I'll say it one more time, right? if the input to the inverse of f is -2, that means it's going to be the output for our regular f of x. So when f of x equals -2, the associated x value for that is 1. Just like that. So this would equal 1. So that's how we do it with the table. And then now I want to look at a graph. So this is number 12 of your review sheet. So there's a lot to this problem. We're going to start with A. So use the graph of g to solve g of x equals 5 for x. So when g of x equals 5, remember, we're talking about outputs here. So our output is equal to 5. That's right over here. We want to find what x is for g being our black line right here. So when g of x is 5, we look right here, our associated input, or x, is 2. So x equals 2. Now here, we have g inverse of 6. So if 6 is the input to the inverse function, that means it's our output for g of x. So when g of x is 6, right here, we want the associated x value. Oh, well, just kind of estimate right there a little bit, right? So the associated value right there is going to be equal to about 4.5. Now this next one, we don't have any inverses involved, right? So g of 4.5 means 4.5 is actually our input, so we can look at our x-axis right here. So when x is 4.5, we kind of just already found it earlier, right? When x is 4.5, our output is 6. So now we are left with r of 6 that we want to find. So when our input is 6, our r, which is our red function, has a value, or an output value of 1. So now we have g inverse of 3. Again, if we're looking at g of x, that means 3 is our output. It's no longer our input. So when g of x equals 3, what is the associated input value for that? That's going to be equal, well, here, let me clear this really quick so we can take a better look. So, right, 3, and it's kind of like, we're just going to have to estimate. I think they estimated to be about 1.25. Now for E, it's simple, there's no inverses, right? We know -2 is going to be our input for R. So when x is -2, right over here, the associated output value for R, remember our red function, we're going to go right here, that's going to be -1. So that becomes our input for G, so we have G of -1, right? And then G of -1, so we're going to look when x is -1. What is our G? Well, that's also going to be equal to -1. Now for F, it says evaluate G inverse of R of -2. So again, we work from inside out. So R of -2, let's figure out what that is first. I'm going to write it on the side just so we're aware here. So R of -2, well, we kind of found that earlier actually, right? That's just going to be equal to -1. So now G inverse of -1. Again, if we're dealing with inverse, that means I want to look at our y-axis here, in this case specifically, which is our output values. So when our y, again, let me clear this from the previous ones. When our y is -1, what is our associated x value for the g of x graph? Well, that's going to be -1. All right, so now for the last one, we have g inverse of g of 2. So we look when x is 2, what is g of 2? That's going to be right here, right? G of 2 equals 5. So now we replace that with g inverse of 5 instead of g of 2. And now we want to look for when our output of g of x is 5. What is our input? Well, we already talked about that. That's just going to be 2. All right, so now we're almost done. We just have, oh, that should be 3.7, right? The difference quotient. So, difference quotient, we brought up average rate of change again, right? So if we look right here, the definition for difference quotient is the average rate of change of a function f on any interval h units long, and it's represented by, well, this simplifies, right? It's represented by this function. Obviously, the x minus x cancels, which is how we get this guy right here. So I kind of want to talk about what does it mean when it says any interval h units long. All right, so let's say we had 2 points. Ignore all the points given on this graph, right? We just have 2 points. And the first point, we know, starts at x. And then we want to find the average rate of change when it goes from x to x plus some unknown value h. X plus, we don't really know. That's why we use h. So what does h mean? Well, h is just the interval in between here. That's h, right? Because x plus h gives us our ending value. So h just represents our horizontal change here, which is why, like, for example, we see x, here, let me write it out, right? F of x plus h minus f of x, because we're going from x to x plus h. So when you do the denominator and you say x plus h minus x, that's just showing that horizontal change for the denominator, right? And then the numerator obviously is going to be our vertical change. But obviously when this simplifies, that's how we get to the h. So again, it should be 3.7. So I know when we went over this example, we were using t, and I think that was getting a little confusing because the t and the plus was getting mixed up. So luckily, this example on your review sheet, right, we're given it in terms of x for our variable. So given that f of x equals 3x squared minus 5x, determine, right, our difference quotient and explain what this expression represents. So this is going to be a little bit of a long problem, and it's a lot of just knowing how to do sort of the algebraic part of the math. So let's get started, right? If we have our difference quotient, f of x plus h minus f of x over h. This is what we want to find. And we're given this function f of x. So the first thing we want to do is figure out, okay, what does f of x, or f of x plus h represent? Well, if we had f of x plus h, right, instead of saying f of x equals 3x squared minus 5x, we're really just going to replace our x's with an input of x plus h. So we would say 3x plus h squared minus 5 times x plus h, right? So now our input is x plus h, which is what we would normally do. Like if this value was 6, we would plug in f of 6, right? And then we would plug that all in. But instead of a number, we're given x plus h, which is why we're saying this is f of x plus h. So now I'm going to go back to this guy, because that was just this portion of it. And we're going to keep rewriting it. So f of x plus h we know is equal to this. I'm going to write that out. So 3 times x plus h squared minus 5 of x plus h. And that's this in pink over here. Now we still have minus f of x. Minus, we already know f of x is equal to this guy over here. So this is super important actually. This needs to be in parentheses because you're doing f of x plus h as one thing minus f of x, which is another. So if you wanted to, you could even put this guy in parentheses as well. So minus 3x squared minus 5x. So all I did is I replaced our f of x with the expression it gives us. And then all of this is over h. And now our goal is just to simplify. Simplify as much as we can. So to start out, we're going to start looking at the left side of the numerator. So we have 3 times x plus h squared. The first thing I want to do is expand this x plus h squared. You can do this either by, like, you might already know what that is, that expansion is. If not, you could do like the FOIL method where you do x plus h times x plus h, or you can do the Punnett square method, which, like, for example, like if you were to do x plus h and x plus h using the Punnett square method, you kind of draw this little square, and these boxes are just what you're multiplying. So this top left box, you're multiplying x by x, which is x squared. And over here, you're multiplying x times h, xh. This bottom left is the same thing. It's x times h, like the row and the column, right? And then this last one is h squared, h times h. Or, right, you can do FOIL. If you did this, either way, if you did it, you would get x squared plus 2xh plus h squared. And that's just adding up all the things inside of the Punnett square, or FOIL. So, with that expansion, we're going to rewrite this. So we have 3 times, right, we expanded the x plus h squared, and we got this guy up here, which is going to be x squared plus 2xh plus h squared. And we still have the minus 5x plus h. And again, you can keep this as a set of parentheses because 100% this part needs to remain in parentheses. Okay, so let's keep simplifying. Again, all of this is over h. Let's move over here, or let's move down here. Okay, so next up, we're just going to multiply. We're going to distribute our 3 to this guy over here. So we have 3x squared plus 6xh plus 3h squared. Then we want to distribute this negative 5 along here. So we would have minus 5x and then minus 5h. Okay, so the reason why I said please keep this in parentheses, because a lot of times if you don't, you will not distribute the negative properly. Like, you need to keep it in parentheses as a reminder that you need to distribute the negative when we're simplifying this expression, right? So this is negative, or when you multiply it, right, it's going to become minus 3x squared, and then negative with the times the negative 5x will become a plus 5x. So, for example, like if you didn't have the parentheses and you had minus 3x squared minus 5x, I think like it's very likely that you would have kept this as a negative 5x and would have thrown your answer off. But in reality, right, you need to distribute the negative, which makes it a positive. So I'm going to erase this. Anyways, so we have all of that over h. And now we can start canceling like things out, make it better, right? We have a positive 3x squared, which cancels with the negative 3x squared. We have a negative 5x, which cancels with the 5x. And then we can write out our remaining terms. So we have 6xh plus 3h squared minus 5h over h. But you're not done simplifying yet, because you can cancel out an h from every term in this expression, right? So you can cancel out your h's, and what you're left with is 6x plus 3h minus 5, right? So I know it's just a lot of math to get here, but That's how you would do it to find what the difference quotient is. And then it says explain what this expression represents. Well, so this guy, right, this is the difference quotient of our function over here, 3x squared minus 5x. And what it represents is, right, our average rate of change of the function f of x. And it's over the interval from x until x plus h. Remember, like if it was real numbers, we usually would say, oh, like it's from 2 to 6. But here it's not, right? We're saying any interval from, or we're saying the interval from x to x plus h with some value of h that we don't know. And so yeah, so it's over the interval from x to x plus h. So I hope that helps. That's going to be the end for the review for Module 3. And please let us know if you have any questions. Thank you.